Welcome to today's podcast. Today we will be focusing on molar mass, percent composition, and empirical formula. You will need a calculator for this, so if you don't have one, you may want to pause now and go get one. All right, chemical equations. So this should be a review. Chemical equation is basically a sentence, so it's describing to us what is happening in our chemical reaction. Reactants are to the left of the arrow, the things you're starting with when you do the reaction, and then the products are on the right of the arrow. Those are the things that are produced or come about as a result of the reaction. Our equation should be balanced, so what that means is you have an equal amount of each atom or each element on both sides of the arrow. Okay, and we have the same number of each kind of atoms on both sides because remember our good old friend, the law of conservation of mass. Mass cannot be created or destroyed. So we have equal amounts of both elements or of the element on both sides. All right, some abbreviations that you'll see, a little S after a formula means solid, G for gas, AQ for aqueous, so sometimes we need to know the state of matter. Aqueous just means it's in a solution with water, so you took a solid chemical and dissolved it into water. So now it's in the liquid form, but it has a chemical dissolved in it. The arrow with heat over it just means that during the reaction you added heat. Same thing for the triangle, that's a shorthand indicating that you added heat. And then if you have a compound or a formula on top of the arrow, that's indicating that you added a catalyst. So remember that the catalyst is not used up in the reaction, so you'll have the same catalyst you started with left over at the end. So we don't write it in the equation because it's not actually undergoing any change, it's not rearranging in any way, it's just helping to change the activation energy, to lower that activation energy to make the reaction go faster. All right, starting off with a review of atomic mass. Atoms are really small, right? So it's difficult to discuss how much they weigh in grams because we'd be using really small amounts of grams. So we use the atomic mass unit. Those are the numbers on the periodic table. So those masses on there are not in grams. They're in AMU, or atomic mass unit, as it says there. So the average of those is on the periodic table. And we know it is not a whole number. It's an average of those weighted isotopes. Okay, and this is just a quick review of that. So the average atomic mass is determined by multiplying the abundance, so taking it out of the percentage and multiplying it by the mass, plus the abundance of the next isotope by the mass, etc. All right, molar mass is the mass of 1 mole, hence the name. So a lot of times that's referred to as the molecular weight, same thing. So when we find the molar mass, that's when we use the periodic table. So that is when you would look at the mass of each element, multiply it by the subscript, and then add it all together. So hopefully there's an example here. Okay, well, not an example, but one's for you to try. So you find the mass of each element and add it, but if it has a subscript, you have to multiply the mass of that particular element by the subscript. Okay, so hopefully you've learned this. So go ahead and pause and try these. Right, here are the answers with the work shown, so you can kind of see if you got it wrong, where you went wrong, what happened. Just like with any other podcast, please, if there's something you have a question on, make a note of it so that you can ask me in class. Don't forget when you have parentheses, the subscript outside the parentheses reverse distribute, but only to the items inside the parentheses. So like this 2 does not go with the CA, okay? This is something weird you've probably never seen. It's called a hydrate, so it means in solution with water. So you would just treat that, the same way you would treat any other molecular mass. What's tricky is this little dot would make you think that you're going to multiply them, but you're actually going to add them. So you just basically think of it as one big long compound, so you're just adding this in. Distribute the 2. All right, percent composition. You may have done this already as well. So you can find the percent of the mass of a compound or the mass of each element within the compound. So you can find out what percent of that compound is made of hydrogen or what percent of that compound is carbon. Okay, and that can be helpful when you're trying to do certain experiments. So the way that you would do it To find the percent of a certain element, you would take the number of atoms of that element, so the subscript, and multiply that by the atomic weight of that element, divide it by the molar mass, which you just found on the previous slide, of the whole compound. And then anytime we do a percent, we always multiply by 100. So here's an example. If we're looking at ethane, which is C2H6, if we want to find the percent of carbon, you're going to take that little subscript 2, because there's 2 carbon atoms, multiply by the mass of 12, which is from the periodic table. Then you find the molar mass of the whole thing. So it's 2 carbons plus 6 hydrogens. So the molar mass of the whole compound is 30. So you do 24 divided by 30 times 100. So it would be 80% carbon. Okay. Review of the mole. So mole is just a number, right? It's a huge number, but it's just a number. So same way that we would say a dozen to represent 12, we would say a mole to represent 6.022 times 10 to the 23rd of anything. It's often referred to as Avogadro's number since he's the one that came up with this. Okay, so if we're looking here, a single molecule would have its mass in AMU, but there would be Avogadro's number of molecules inside a sample if it's 1 mole. So 1 mole means you have Avogadro's number molecules. So if there's 1 mole of water, you have 6.02 times 10 to the 23rd water molecules. Okay. We used carbon-12 to come up with the AMU system. So 1 mole of carbon-12 actually has a mass of 12 grams. So that is where the system, the AMU system, came from. We used carbon as the base. All right, so you need to be able to convert between moles and grams. So you use the molar mass to do that. And then if you have the moles and you want to find the formula units, which is what we say if it's ionic, or the molecules, or the atoms, if it's a single element, you use Avogadro's number to convert between those two. Okay. We're not quite in stoichiometry, but it is coming very soon. So there are going to be some little like one-step type conversions that you'll be doing today. Okay. So it says moles provide that bridge that take us from able to go from molecules or formula units to grams and vice versa. All right, empirical formula. So get your calculators out and ready if they're not already out, which they should have been since you already did molar mass. So it says empirical formula for a substance shows the lowest ratio of atoms. So it's the reduced version of the formula, and it's based on a mole ratio. So ratios can be reduced, like you've learned in math, ratios can relate 2 or more numbers. So we can calculate the empirical formula, and we use the percent composition. So usually you'll be given that percent composition, and then you use it to calculate the empirical formula. When we do these, we always assume that it's a 100 gram sample. So because of that, we're able to just take our percentages and assume that they're the same amount of grams. And you'll see what I mean by that. So what we would do is take our grams, use the molar mass, and convert it to moles. And then we will find the mole ratio, and using that ratio, we can reduce it and get that empirical formula. So here are the steps, and we are going to do some problems. So as mentioned, because we're assuming 100 grams, you write whatever percentage they gave you as grams. So if it said it was 45% carbon, you would start out by saying 45 grams of carbon. Convert the grams to moles for each one. You're having a bunch of little one-step conversions for each element that you have. And you divide all of them by your smallest mole value. So whatever you get when you do those conversions, the smallest one, you're going to divide all of them by that number. So that this way, that one at least cancels out to 1. If you have any decimal answers, you're going to multiply until you make it a whole number. So if it comes out to like 1.99, that's 2, right? Just round that to 2. But if you get a weird decimal that's kind of in between, it's not really close to any whole number, then you need to multiply until it becomes a whole number. So for example, if one of them after you do your division is 1.5, we can multiply that by 2 to make it a whole number of 3. but you have to multiply all of them by 2 then. So if you find yourself in the case where you have to do this multiplication to get a whole number, you would multiply all of your elements by that number. Okay, you don't see this too often, but it will come up from time to time. All right, so here is an example. The compound para-aminobenzoic acid, you may have seen it listed as PABA on your bottle of sunscreen, is composed of carbon at 61.31%, hydrogen at 5.14%, nitrogen at 10.21%, and oxygen at 23.33%. Find the empirical formula of PABA. So what we need to do, like we said, we're going to assume 100 grams for each one. So these are simply the percentages, but now we are just writing them as grams. So instead of 61.31%, we're saying 61.31 grams. And for each one, we are simply converting it to moles. So if you forget how to do that, this could easily be the little box. Like I know I did the box in class. It's the same thing. So you'd have your grams on the bottom, and then 1 mole, because this is the molar mass, so it tells you how many grams for every 1 mole of carbon. So this number is coming from the periodic table. We are just dividing, so 61.31 divided by 12.01, and that's going to give us 5.105 moles of carbon. So you do that for each one. You just find the molar mass and divide by that molar mass, okay? Then what you need to do is take them and divide them all by the smallest value. Okay, so if you look at our answers, our nitrogen gave us the smallest amount of moles, 0.7228. So you're going to take this divided by 0.7228, take this divided by 0.7288. Sorry, I think I said 228 before. And take this and divide by 0.7288. So that's what you're seeing here. We're dividing each of those amount of moles by the smallest mole value. So dividing all of them by 0.7288. And you can see they come out really nice and close to these whole numbers. So most of the time, they're going to come out close to a whole number. As mentioned before, it could give you a decimal, and then you have to do a little extra work to try and multiply it out into a whole number. This one, we don't have to worry about that. So we can see 7, 7, 1, and 2. So then we just write those as the subscripts. So C7, H7, N, O2. And that is our empirical formula. Okay? So here's one for you to try. The answer will be shown, but what I would like you to do right now is pause so you can try this on your own. You can look back at the example that we just did if you're not quite sure where to go, but I would like you to pause and try this one on your own. Okay, so here's the work. So step 1, convert them all to moles. So we divide each one by its molar mass. Remember that we're just simply putting the percentage into grams and then dividing by the molar mass. Okay, and these molar masses are coming from the periodic table. Then divide all of them by that lowest amount. So 1.202 is our smallest. So we're dividing each of them by 1.202. And that's giving us 1, 1.004, and 2. Oops, sorry. And then lastly, you just rewrite out the formula. So this is the same information that I had at the bottom of the last slide. Okay, the numbers that you get after dividing. Once again, they're very close to whole numbers, so we don't have to try and multiply them out. So it's just K, C, O2. So that's how you do empirical formula. Okay, this one I'm going to put into the next podcast because the podcast creator that I use only allows us to do 15 minutes at a time, and I'm at just over 14. So check out the second podcast to learn how to put them into a molecular formula.